those who don't know me, my name is Phil Wallace and I'm the chairman of the Cardiff Society, which I have somehow been doing for 8 years now. Still not sure how that happened. Before we get started, a couple of minor housekeeping things for you. If you could please keep yourselves muted during the talks. If you have a question you'd like to ask during the course of the talks, please type it in the chat and we will do the Q&A when we get to the end of the second talk. Now, in the previous sessions, we've gone over some of the basics. We've looked at stars, the wider cosmos, space exploration. Now, however, we are looking backwards in time, not with a telescope, but we're looking at where astronomy came from. It is, after all, a pretty big topic, and it doesn't just sort of appear in a puff of logic. So, speaking on this this evening, covering the first 2.5 millennia or so of astronomical history, will be Gordon Drury. Now, Gordon, he holds degrees in electronics and humanities for some reason. He started his career working in telecommunications R&D, including 3 years at the post office, what is now BT, developing digital satellite communications. He made regular visits to the Goonhilly Downs Earth Station down in Cornwall, which is now an important part of the NASA ESA Advanced Deep Space Network. And Goonhilly, perhaps not Gordon, were directly involved in the recent Odyssey moon landing. Excuse me. In 1974, he moved to digital broadcast engineering, research and development, publishing papers on video and audio coding, recording and transmission, and worked for several international standards groups. He then retired in 2001 to take up commercial consulting work, as well as advising charities and government consultative groups on new media technology. So I suppose we can blame him for the rise of Facebook everywhere. He is a retired fellow of the Institution of Engineering and Technology and of the Royal Television Society. And his main technical interest is in astrophysics and is involved with a local group that continues Dr. Rodney Hillier's work in adult education. So, Gordon, over to you, please.
Okay, I've called this talk, as Phil says, it's a long period of 2,500 years of history. So we're not going to do it in intimate detail. We're going to see the high spots that got us to where we are. I've called this part of the talk, and I guess it applies just as much to James later on, the shoulders of giants. Well, we have only learned what we have learned about science in general by standing on the shoulders of people in the past who have done some basic work that have added to our collective knowledge of the world we live in. And this is the quote that the shoulders of giants came from. It's a sentence out of a letter that Sir Isaac Newton wrote to his colleague, Robert Hooke, both the fellows of the Royal Society. They didn't get on too well, but this letter was written at a time when they seemed to be getting on reasonably well. They were complimenting each other, which was a bit of a change. The question for us this evening is, whose shoulders were they? And if you notice, there's a spelling mistake in the yellow. Well, actually, that's the way Newton spelt it himself. So I've given you both, the modern one and the Newtonian one. Anyway, let's get on to business. Let's go very quickly through the earlier stages of observation and try and imagine that you are in the Serengeti Plains or something, and you know nothing about astronomy at all. But you do know about the sky. You see it every day, and you know that you're standing on the Earth. We've looked at the sky for millennia as a human race, but never really got to grips with it. We know about the Earth because we live on it and it's accessible to us, whereas the sky is not. We see it, but we can't actually engage with it other than what we are seeing with our eyes. We seem to be at the middle of it because everything seems to be moving around us. Now, we know today that isn't strictly true because it's the Earth that's moving and not the sky. So let's stick with the ancients for the moment and accept that we are, at this point in the talk, literally the center of the universe. What can we see? Well, we can see the sky, but we are limited in what we can actually see at any one point, like this particular red spot here, for example, maybe somewhere in southern England, and the white line shows you your horizon. You can only see what's above you and above the horizon. If you imagine the Earth is a pure sphere, of perfectly smooth sphere, and you are 2 meters tall, which is roughly the height of, well, at least it's not average, it's a little above average height, your horizon is actually only 4 kilometers away. So you can't actually see a great deal of that sky, but you are helped because the Earth is moving. I know we said it wasn't, but the sky is moving, so it sweeps around you. So the movement of the sky helps you see more than you can actually see at any one instant. The other problem we have, apart from the horizon, is that there's an atmosphere. We know that, but the ancients didn't. There's an atmosphere between us and the sky. Fortunately, unless there's cloud around, the sky is visible to us because the light we see passes through that atmosphere reasonably cleanly. Okay, so what do we actually see? Let's see the details. You've learned about suns and stars. Well, we have a sun and it appears during the day. Well, it's called a day because that's when the sun's there. Similarly, most nights you see a moon, but the moon doesn't appear every day. It's there for roughly 28 days in a cycle. So there's an oddity, and it disappears occasionally and comes back again in a peculiar way. So you get half moons and part moons, crescent moons, and so on. The stars, as you well know, are best seen at night because it's dark and then you can see them better. But they are there. There are stars in the day. It's just that the sunlight is so bright you can't see them. The other visitors we have to our world in the sky are transient in the form of comets, which you've heard of earlier in this course, but also meteors and other things. And there are aurorae in the north, particularly the aurora borealis in the north. There are strange lights in the sky from time to time. Well, that puzzled the ancients as well. So that is a kind of background to where humans first began to think about and view and try and explain the sky. Now, we can only see what our eyes can see. And that means we only see the brightest objects that are up there above us, and objects that emit light naturally, which are suns. But in the early days, they didn't think about emission and reflection. They thought the stars were reflecting the sunlight. We know that's not true, but that's what they thought. And you've heard about the electromagnetic spectrum earlier in earlier talks. Well, we can't see much of that at all. It's a tiny, tiny part of the whole gamut of radiation that we could use. Some of it's trapped by the atmosphere, so we can't get at it. And so we always need instruments to make measurements. And you heard last week that only in the last 60 years have we been able to get above the atmosphere with probes that John talked about last week to be able to see and build the knowledge we have today. Now, back in the day when we were beginning to walk, as it were, as astronomers, we thought differently about the heavens. The speculation about what was going on up there wasn't necessarily scientific in the sense that we know it. It was based on myths, superstitions, in other words, explanations that they made up as stories rather than anything else, religions even, and there emerged a class of what we might call magicians who claimed to know the meaning of the events that were seen above our heads. Why does the sun do what it do? Why does the moon? I know this, and I'm going to tell you, and that gives me power. And the biggest power of all of these magicians was the ability, or they claimed, an ability to predict the future. This is incredibly valuable if you're a king or a ruler or something like that. And effectively, it became what is known today even as astrology. Now, if you talk to an astronomer today, he'd be very upset if you called him an astrologer. But way back in this time, they were indistinguishable. The study of the sky, or astronomy, was intimately connected with what it could tell us, what the sky is telling us about events and even ourselves. Well, you know about the zodiac. It's, some of you may look up your stars in your horoscopes in newspapers and so on. Well, that was the beginning of the division of the sky into sectors, which we still use today. 12 of them, 12 houses of different shapes and sizes of star clusters. Now, here's some of them. I'm only going to pass them too quickly. We saw patterns of light in the sky, and we imagined shapes of real objects and creatures And the two examples here are Orion, which is very distinctive in the sky, and the Great Bear, which is another one that's very distinctive in the sky. They all appear to be in the same place, but they're not. If you look at Orion, for example, Bellatrix, which is the one here, is 250 light years away, roughly, whereas this one, which is called Tabit, is only 26 light years away. So it can't possibly be in the same place. And you can imagine the same with these other ones. This one here in the middle, I think that's Alnitak or Alni. I can never remember which is Alnitak and Alnilam. One in the middle of the belt. Anyway, that's nearly 1,400 light years away. So again, it can't be in the same place. And yet, if you go across here, the other side to the Great Bear, you see they are much, much closer than the clusters, the main clusters of stars in Orion. So we mustn't blame these people for thinking they're all in the same place. They just did because they had no evidence pure otherwise. And of course, we know, well, we can say that the sky that we see is much the same as the sky our ancient ancestors saw, because not a great deal has changed. However, this effect of what the sky had to say to us was immensely powerful in these early societies. Stonehenge is only one example of massive ancient structures that are very strongly connected with astronomy. The alignments of the stones, etc., which I'm sure you all are aware of, but many others are found everywhere. The obvious ones are the pyramids and so on. Well, these people invested huge amounts of effort and energy in order to build these things, and we have to try and imagine why they did it and how they did it, where the resources came from, all the man hours and all the rest of it. But we have no written records that help us. All we've got is the artifact of the thing itself, like Stonehenge. Now, we do have some help when we get closer to about 5 to 6 or 700 BC, because there are tablets, Babylonian tablets, that tell us about certain astronomical events, in particular Halley's Comet. But there are biblical and Islamic scriptures as well that refer to objects in the sky. The Anglo-Saxon Chronicle also mentions events. It doesn't explain them. It just says they happened. This strange thing passed through the sky, and so on. So these are observers, and that's an essential part of astronomy. Observation is the key to what else we know about the world around us. And as Jane said last week, observations always trumps theory. So remember this as we go through the evening, that the observations are the most important part. Our problem is fitting a model that tries to explain or predict that explanation. So where's the explanation going to come from? Well, there wasn't one until about the time of Aristotle, roughly 300 BC. A cosmic model had evolved by this time. It was called the music of the spheres. We can't go into it too deeply because there's not enough time. But the Greeks imagined that the sun and the moon and the fixed stars, the ones that don't move, and the stars, well, they thought they were stars, but they were actually planets. They didn't know that, but they were the wandering stars, orbited the Earth. We were in the middle, as I said earlier. Everything moves around us. And by the way, the Earth is made of stuff. And their elements, not our 92 elements, are earth, fire, air, and water. And all those things make everything beneath the moon. If you look here, the closest orbiting object to us is the moon. Under the moon was called sublunary, and the earth and the water and the fire and the air were all sublunary. Everything else was extraluminary, including all the planets. Now, we can't go into it in any detail, but they clearly knew which planet was in which orbit. You see here, they're all here. Mercury closest to us in this model, and on the other planets. But how did it work? Well, everything is turning because there are, beyond the fixed stars, which are all on the same sphere, exactly the same sphere, equidistant from us and the Earth, is being pushed around by the angels. They were called the fixed stars. And there was a mechanism that caused the outer movement of the stars to link to all the other orbits. So like a kind of geared clockwork, everything turned round. And that was the model that was accepted. And by the way, earth, fire, air, and water were the things that made up the sublunary world, but everything in these spheres was made of something called quintessence, their fifth element. Now, it's highly idealized. It wasn't based on objectivity. It was all philosophical, or very much philosophical, with no real connection to observations at all. Despite this, this model lasted for centuries, even as far as Kepler in the 17th century, in the middle of the 17th century. But the strength and the reputation of Aristotle here on the right was such that it underpinned this model for centuries, as we've seen. Now, some later Greeks after Aristotle, one called Aristarchus, and if you remember the intro video, there is a crater on the moon called Aristarchus. Well, he didn't actually believe in this model. He believed that the Earth wasn't the center of the system. He believed that the sun was, but no one took much notice of him. The model he proposed wasn't really accepted, but the others like Eudoxus and Hipparchus, the three of them and others weren't actually taken with this model, but they couldn't come up with anything convincing for their colleagues to accept. And the big model is the features of this model are perfect circles, everything moving at a constant speed on a circle. Okay, now that we know that model actually doesn't work, because we come to a very famous astronomer who had moved 500 years when nothing much happened until Ptolemy comes up with his big work of synthesis. He brings together all the knowledge of the ancient world, takes any observations that he's managed to find, even as far back as the Babylonians, and used it to make a big book. Now, it's generally known as the Almagests. Well, that's an Arabic term. We'll come to that shortly. The Arabic term Almagest means the big thing, or the greatest. And what he did was build this massive book in which he described the mathematics of this big circle. And it lasted for literally centuries. This is a repeat. On the right, you see a graphic that came out of a book published in Antwerp in 1539. It's still there. If you look at it in detail, you'll see there's the moon, Mercury, Venus, the sun orbited the Earth. And beyond the sun was Mars, Jupiter, and Saturn, because they didn't know any other planets at that time. And so even though this was written in about 150 AD, it carried a huge amount of weight for centuries, more than 14. It retained the Greek model we talked about earlier, with the celestial objects orbiting the Earth at a constant speed in perfect circles. Trouble is, Ptolemy discovered it didn't work too well. He tried to match this model with using geometry, and he found that the observed data he had didn't actually agree to it. Now, we said observation trumps theory. So what's got to give here is the theory. He didn't succeed because his theory wasn't right. There is a possibility, however, that some of the data was a bit dubious. And there's an American astronomer who wrote a long paper in 1977 who thought that Ptolemy had fiddled his data to make it fit his model. Well, that was been knocked down by somebody called Owen Gingrich. We haven't got time to go into that, but there is a point here which says, are you sure your data are correct? And in which case, how good are your observations? How good are your instruments? And how good are you at recording everything and making sense of it? Ptolemy, in the book, there's a large amount of mathematics in the book. He had to adjust his model in order to explain what was seen. And one major issue for him was a thing called retrogression. Retrogression is from the Earth, is a visible sign that the planets don't actually continue in a constant circle. They actually go backwards occasionally before going forwards again. Now, this is better explained when we've got our own modern model of the heliocentric solar system, where the sun's in the middle. It's a lot easier to explain. And so here we have a position of the Earth coming up in position 1. Well, Mars is in its orbit, which is roughly twice as long in time, the period. And if you look from the Earth at Mars, you see it projected against the fixed stars. They don't move. You have to assume that they don't move. So as the Earth moves around like this, it's going faster, so it's catching up with Mars. And so the apparent position of Mars in the sky changes. So it's when the Earth is at 1, Mars seems to be here. When the Earth is at 5, it seems to be there. But the bit in the middle, it makes it look as if it's gone backwards. And the same thing happens to the other planets. I haven't done Jupiter. This is not the scale, by the way. It happens to Jupiter as well and Saturn as well. So they all of the outer planets do this regression. So Ptolemy has to go back to the drawing board and comes up with this model which uses epic cycles. Now here's an epicycle, but this is the basic Ptolemy model. Earth in the middle, planet going round on its orbit, circular orbit. It's called the deferent, and that's the one that doesn't work. So he adds an epicycle. An epicycle is another circle, such that the planet is circling around a point which is itself circling around the deferent. And if you look at it and imagine how it's going on, it kind of tumbles around the deferent circle. And the path in the sky looks like that. And so between 2 and 3, that's where you see the regression, where the planet appears to go backwards before going forwards again. Well, there was another little problem, was that in the observations, it wasn't just the regression. It seemed to need that the planet has to go a bit quick, or the center of the epicycle has to go a bit faster at some points in the orbit and slow at other times. Well, Ptolemy came up with his wheeze. We haven't got time to go into it in detail, but he moved the center of the deferent to a place called the eccentric. And so the Earth was offset to one side, shown in green here, a distance I've called B. But he also introduced another point, an imaginary point called the equant, around which the planet appears to circle. It doesn't go around the Earth anymore, but he kind of fiddles it and says, well, it's all circles, isn't it? So it must be okay. And it does match the observations I see. So it must be okay. So for him, his model worked because it met more or less the observations he had. Now, the complexity of this thing is such that some of his contemporaries possibly didn't agree with him, but because of the power of the book, it was an immensely rich book in terms of theory and so on. It lasted for centuries until we get to the Islamic age, which was about 1250, and a scientist called Al-Tusi simplified this model, got rid of that equant and all the rest of it, but it didn't quite work. Now, the story of the Islamic world and its connection with astronomy is you can see it in a number of books. This is one of them, which is one of the classics. And in here, 600 years beyond Ptolemy, the Islamic world woke up to the value of astronomy, and particularly its astrological value. So we haven't separated the two disciplines yet. They had conquered most of the Middle East, and they were settled by about 750 AD. And one of the big caliphs set up this thing called the House of Wisdom. It was a bit like Ptolemy's Almagest. He collected all the scientists, all of the expertise from as far, well, from the Greek world, which they inherited, but there were Chinese, Indian, and Iranian sources that influenced the way Islamic scholars curated all the knowledge they collected from the ancients and literally curated it. And the Muslim rulers, the ones who supplied the money to set up some of these houses of wisdom, and we'll see in a bit, observatories, wanted science because they needed expert knowledge to run this vastly growing empire that they were building, but particularly astrological predictions. They required it because the Quran, the holy book of the Islamic world, required every Muslim to pray at particular times of the day. And also he had to pray pointing in the direction of Mecca. Now, imagine how you do that without a lot of scientific and particularly astronomical knowledge. But they had it, and the mosques would have someone who was a timekeeper. He was called a muwakit. He kept time, and the muezzin, who was the one that called people to prayer. They knew about longitude and latitude, and they were found using instruments, one of which was the astrolabe. It's a very sophisticated instrument. I'm not going to say anything in detail about it, but I would recommend you to have a look at this instrument because it was the basic instrument that the Islamic world used for its observations. Two people are important. Al-Battani of that period, he was Turkish, and Al-Sufi, or Az-Zofi as in the Latin world, who worked in Isfahan in southern Iran, wrote a treatise on the subject, and he found 1,000 uses for one of these instruments. It's an incredible thing. And over the centuries, many other Islamic scientists, astrologers, I keep having to use that word, and they came in all shapes and sizes. They never used telescopes. If you want to know more about it, you can pick up these two YouTube descriptions of it, but it's a fascinating instrument and well worth a look if you're interested. Another big name in the Islamic world was Al-Sufi. He wrote a very large, comprehensive book. He had studied the skies, mapped the constellations, and here's one picture from his book of fixed stars of 964. It refers back to the Almagest, but Al-Sufi added a great deal of detail, particularly better observations, and this is one of his maps.
2 minutes, please, Gordon.
Okay, and it ended up, if you look at this particular constellation of Orion, all of the stars have got Arabic names. You'll also notice that Betelgeuse is red because it's cool, and some of the others are blue because they're hot. And we have dissent now in the Arabic world which says, we don't believe this, and this Almagest just doesn't work. And they're beginning to work in other fields of science as well, like optics. This man wrote a book on optics and was doing studies that were only revived 600 years later by Huygens and Newton. The money, the astrology generated the money from the rulers to build big observations. And this is an artistic impression of one at Maraga, which is in northern Iran. It doesn't exist anymore because it fell into ruin after the funding ran away. How familiar is that? The first one on this site was built for the famous poet who was an astronomer called Umar Khayyam. And that was done in about 1070 or 1080 odd. It didn't survive the Shah's death, the man who paid the money, in other words. And when he died in 1092, it fell into ruin. Nevertheless, the idea was still bouncing around the world, and we had 200 years later, this famous school in Iran, in Isfahan, was run by this Al-Tusi person. The new sponsor for this one, where did the money come from, was a man called Hulagu, who's the grandson of Genghis Khan. So these are the period of the Mongol invasions of the Middle East and Far Eastern of Europe, east of Europe. But to continue his patronage, he had to play on the interests of the astrology. And here again, the Islamic world was effectively widely involved because the scientists that worked here came from all over the Islamic world. The instruments were built by old
time.
Sorry?
Sorry, Gordon, we've run out of time.
Okay, well, that is where we come to in the end of the Islamic world. And this is what Copernicus picked up. We'll skip this. Copernicus changed the direction of it all because the Islamic world fades away and scientists in Europe start to pick up on the work of the Islamic scientists and started to think about it again. And here, the famous statement by Copernicus was, actually, the sun is at the center and not the earth. And if you change the positions, suddenly the observations all make sense with a very simple model. Now, he got into trouble much later, long after he died, because when Tycho Brahe started measuring things in Denmark and later in Prague, he had some very, very good.
Gordon,
yeah, okay.
Sorry, we really do need to move on, I'm afraid.
Okay, well, here's a summary then.
Right. Well, thank you very much, Gordon, for that slightly accelerated, admittedly, 2,000-year history of astronomy. Now, to bring us into up to the modern day, we have Dr. Jane Clark, who has spoken, is this 2 or 3 of your talks so far, Jane?
This is number 3.
This is number 3, right. In that case, I won't give her the full introduction as you'll have heard it before. Suffice to say, she has her PhD in physics and an MBA from Warwick. She's been fascinated by astronomy and photography since she was a teenager. I won't say when that was for her sake, although more with a focus on photography. Since she's retired, however, and she then acquired a telescope, her interest has ballooned considerably, and she has now managed to achieve her ambition of having her observatory in her back garden. She is a active member of the Bristol, Cardiff, and Newtown Astronomical Societies, and was a founder member of the West Norfolk Astronomy Society, which we shall have to compare notes about at some time, given where my parents live. And she talks to astronomy clubs, schools, and other societies such as Scouts, Cubs, church wives groups, and the University of the Third Age. I'm not entirely sure what that is, but it sounds intriguing. So, Jane, over to you.
Okay, so I'm going to talk about the scientific age. Where we left off was with Kepler discovering the solar system as we know it. But Kepler could only have done this with Tycho Brahe's data. And Tycho Brahe was the last great pre-telescope observer. He died 10 years before the telescope was invented. And the models that both Ptolemy and Copernicus have made were not accurate enough to fit the data that he discovered. And in fact, Copernicus was less accurate than Ptolemy. And so this is a classic example of how observations drive the development of theory, because Kepler basically faced a start of the 16th century crisis in cosmology because he had to develop a new theory to fit Tycho's data. Now the observational challenge, as Gordon mentioned, was this business of this is over against the starry background over one season. There's Mars, it goes there, comes back on itself and goes round. And it also goes up and down a bit because it's not, it doesn't orbit in precisely the same plane as the Earth. And I observed this epicycle of Mars myself, and it's not a difficult thing to do as an observational challenge if you ever fancy it. And where we left off was with Kepler's laws of planetary motion. And the first of Kepler's laws is that the planets orbit in ellipses with the sun at one focus. There are two points in ellipses, inside ellipses called focuses. So they don't orbit in circles, and the sun is not at the center. If you look at the coordinates, that's a distance of 1, and this has the same shape as the orbit of Mars. You see it's less than 1 on that side and more than -1 on that side. So or more than the absolute value of -1. And so the sun is not at the center of the ellipse, it's at a focus. And Kepler's other laws were that orbits sweep out equal areas in equal time. So if you put an orbit there at that time, and then it's there at that time, draw an area between there, and there, and the equal areas get swept out in equal times. His third law, it starts to get a bit mathematical at this point, I'm afraid, is that the square of the time it takes to orbit is proportional to the cube of the major axis of the ellipse. The major axis is the longest side, which is that, or the longest length, which is that diameter there. Now, Galileo was a contemporary of Kepler's, and he was the first great scientist to use a telescope. His observations showed, even with the telescope, showed even more clearly that the Greek theories were just plain wrong. Because, for example, he showed from the phases of Venus that it must orbit the sun, not the Earth. He developed those laws, which nowadays are known as Newton's laws of motion. Certainly the first two of those laws, Galileo himself developed from experiments, even though they're named after Newton. But Newton himself was really the great synthesizer. He took all these ideas that were in the air at the time. There were nascent ideas about calculus, but he developed them to the point where he could do something useful with it. From Galileo's data, he worked out the 3 laws of motion that, you know, school kids of a certain age know and love. The idea of the law of gravity was kind of floating around. I mean, there was a Frenchman who had it, and there was Robert Hooke had it as well, but none of them could provide a kind of, mathematical justification for it. Whereas Newton synthesized a system of mechanics from all this that described the solar system. And that was kind of the crowning glory of this effort to discover the solar system. The history of it, which I've gone over in 2 seconds flat, is in my book here, and I've donated copies of it to both BAS and CAS libraries, so they're there for you to borrow. The next step, there are 2 parts to it, a theoretical part and an observational part. The theoretical part was what I call the first era of mathematics. The second era of mathematics is now. But the great mathematicians of the ensuing 150 years developed the science of mechanics, Lagrange, Laplace, and as far as astronomy is concerned, above all, Gauss. So that's Lagrange, that's Laplace, and that's Gauss. They developed celestial mechanics, the mechanics of heavenly bodies, enough to determine the orbits of newly discovered bodies. And Gauss went from a promising student at university to a world-famous celebrity within the scientific world when the asteroid Ceres was discovered, and somebody made a handful of observations of it. Then it disappeared behind the sun. And obviously, they didn't want to have to rediscover it from scratch. And famously, Gauss took the challenge, accepted it, and came back very quickly and said, "This is the orbit. This is where you should look for it." And they found it. And later than these 3 guys, people even discovered the planet Neptune by calculations from the perturbations of the orbit of Uranus. So, mathematics was playing a great part in the unraveling of what we knew. The observational part of the next stage was better telescopes. The revolutionary stage was the first telescopes were invented in Holland. Galileo was a spectacle maker who very quickly heard, I mean, among other things, he had all sorts of businesses on the side. He was quite a polymath and an entrepreneur. But he had a spectacle making business, so he had the lenses kicking around. As soon as he heard about it, he made a telescope. And then Newton invented a reflecting telescope. Those were the revolutionary stages. From there on, it's been mostly evolutionary. The Herschel family, that was their biggest telescope, but they kind of worked their way up. They discovered Uranus. They discovered invisible infrared light. And William did this. But William made the first attempt to delineate our galaxy. His sister Caroline was the world's #1 comet discoverer. And in her day, she was quite a celebrity in demand in high society because of this feat. And William's son, John, mapped the southern hemisphere sky. He went to South Africa to do this. And he produced the first drawings of nebulae and galaxies, which look kind of like what we see now. A Frenchman named Charles Messier catalogued the non-stellar objects. He was a comet hunter. And basically, it was a case of, no, I'm not going to be fooled by that one again. So he produced a list of 100 objects that were not comets. And Friedrich Bessel first successfully measured the distance to a star. If any of you have done a degree in anything mathematical like physics or maths, you'll know that he was a mathematician as well. The next big change was the era of spectroscopy, which began in the middle of the 19th century. It completely revolutionized all sorts of science, not just astronomy. The key discovery was that the spectra from astronomical objects and some objects you measure in the laboratory are not continuous like this top one here. They either have black lines in them, absorption lines, or at the same frequency, therefore, or wavelength, and therefore the same color, there and there, they have emission lines like that. Those emission lines tend to be what you detect in the lab. Absorption lines tend to be what you detect in stars. And from this, people figured out gradually, with a lot of hard work, that you could decode the positions of these lines and identify chemical elements. Why was this? Well, it wasn't fully explained until the advent of quantum mechanics discovered by Heisenberg, who worked in a spectroscopy department in a university. Spectroscopy can also measure temperatures and speeds of celestial objects, and is now an absolutely vital tool in astronomy. There's a quote that I gave last week that professional astronomers never use telescopes without spectrographs, amateurs never use them with. And neither statement is quite true, but they're pretty close to the truth. So spectroscopic discoveries. Helium was first noticed in the sun spectrum by this gentleman, Jules Janssen. Cecilia Payne-Gaposchkin discovered that the sun is mostly hydrogen from examining spectra. And Edwin Hubble, by measuring speeds from spectra, discovered that the galaxies are moving apart. So just about everything that we know about stars and galaxies has been determined by this technique, spectroscopy. Now, with stars, it was discovered by two people called Hertzsprung in Europe and Russell in the United States, that if you plot a graph of the brightness against the temperature or color, which is a good proxy for temperature because the hotter things are, the bluer they are, stars don't just randomly appear all over the place on this graph. They actually appear in fixed places. This is the main sequence, which is the bit that Hertzsprung and Russell first discovered. And you get a population here of giant stars. It's a rather smaller population, but it exists, and they tend to be reddish. And another population of what get called supergiants. But you even get very hot supergiants, which are blue. And down here, you get a completely different spectrum, or a set of stars called white dwarfs. They're a lot less bright, but they're pretty hot. I mean, the sun is there, and the surface temperature of the sun is about 6,000 degrees. Surface temperature of a white dwarf is anywhere between 10,000 and 20,000 degrees. So, they're pretty hot. Arthur Eddington was at Cambridge University, early 20th century. He discovered that nuclear fuel burning was the mechanism that kept the stars burning. Hertzsprung and Russell discovered this diagram. Eddington again, and a guy called Emden before him, but I think it's mostly Eddington, developed a mathematical theory of stars, which has been improved, but I don't think it's changed a lot in the last 100 years. I don't think it's likely to. It's a very good theory. And white dwarfs were explained by Chandrasekhar, who it is said that Chandrasekhar himself gave some credence to this story, that Eddington didn't believe him about white dwarfs because he wasn't white himself. And so he emigrated to the United States, where he was given a fair hearing and went on to do a lot more work and got a Nobel Prize for it in the end. So the moral of that story, as far as Cambridge University was concerned, was don't be a racist. Galaxies. The first attempt to characterize the Milky Way was William Herschel, who did some careful measurements and worked out where most of the stars were that he could see. Lord Rosse in the 19th century produced the first high-quality drawings of galaxies. In the early 20th century, this 100-inch Mount Wilson telescope. Now, to put that in context, a big amateur telescope is like 10, 11 inches, maybe 12 inches. So 100 inches is 10. Well, my telescope, which is a pretty good one, is 11 inches. So this is 9 times the diameter of my telescope. And that gave us the first high-quality photographs of galaxies. Henrietta Leavitt made the first extragalactic distance measurement to stars. That's wrong. It's the Small Magellanic Cloud that it was in. And this guy, Edwin Hubble, was able to use Leavitt. Leavitt developed a law for measuring distance, and Hubble used Leavitt's law to make the first distance measurements to neighboring galaxies, which was the Andromeda Galaxy M31 and the Triangular Galaxy M33, which are nearest big galaxies. And he showed that they were so far, they had to be so far away that they could not possibly be inside our galaxy. I said the 1900s and the 1910s, people were beginning to work out distances within our galaxy. So Hubble showed that they were outside the Milky Way, and he also made this amazing discovery that galaxies are moving away from one another. Now, with the so-called Big Bang, that was developed in the shortly after World War II, and the distance measurements. This is a quantity called redshift, which is a proxy for distance, and this is the brightness, which is again a sort of a proxy for distance. And what it shows is that the brighter they are, the more redshifted they are, so the faster they're moving. And we now know that the expansion rate is accelerating. There was a Nobel Prize given in the late 2010s for that discovery. So that's a fairly recent discovery. And the point is that if you say, okay, they're all moving apart, what happens if we kind of quote unquote run the movie backwards? Well, the answer is that they were all in the same place about 14 billion years ago. So it appears that there was an event 14 billion or so years ago at which they all flew apart. We now understand that the galaxies themselves are not moving through space. It is space that's expanding and increasing the distance between galaxies. Now, does space within the solar system also expand, or within our galaxy? Most people will tell you no. But actually, I've seen papers quite recently published which argue that actually there is expansion within even the solar system. So that's an open question. How am I doing for time, Phil? Am I all right?
Sorry,
am I all right for time?
Yeah, you've still got 10 minutes. Yep.
Oh wow. Okay. Well, I'll finish within that. Right. The Big Bang. What's the evidence for it? The first bit of evidence is that the galaxies are moving apart. The reddening, I've already explained, the reddening seen in spectra, and red light is longer wavelength than blue light, and light is, the space expands, light stretches with it, so that increases the wavelength. That discovery was made, Slipher began it, but Hubble really did the donkey work in putting this idea forward. The next bit of evidence, I mean, I can't go right through the mathematical arguments in detail because it's a bit complicated, but well, I mean, I could, but you know, not in 20 minutes. The cosmic microwave background radiation is not expected in the steady state theory. It just fails to predict it. The Big Bang theory does predict it, and it was predicted in 1948 and found in 1964. So that's 16-year interval. And in fact, Penzias died the other week at the age of 90. So that was one key bit of evidence, is the cosmic microwave background radiation. And I think Alpha, Herman, and Gamow predicted a temperature for it of 10 degrees above absolute zero or thereabouts. They found it was about 3 degrees above absolute zero. But the general consensus was good enough. The Big Bang theory also predicts the ratio of the amount of hydrogen to helium in the universe. And the Big Bang theory predicts 24%, and we observe 25%. So that's a very good prediction. Whereas the steady state theory requires a universe hundreds of billions of years old to make that much helium. And we just don't see any evidence of this. The universe has aged and matured detectably in the last 14 billion years. I mean, quasars in the early universe discovered by these gentlemen were the first example of that, but there's a whole lot of other examples. 10 billion years ago, we now know that stars were being formed at a much greater rate than they are now. New stars are not being produced as fast as they were because the galaxies have, in some sense, matured. So that brings us to the modern era, which is the era of big science. Science is no longer dominated by lone geniuses like Isaac Newton and Einstein and Kepler and Tycho Brahe and Galileo. What you get nowadays is huge collaborative teams. You also get huge telescopes. Many of them are above the atmosphere in space. I think there's something like 50 big telescopes being put up in space. And on the Earth, the main professional instruments, like down here in the bottom right, they put them on top of mountains to get them. They're above most, but not all of the atmosphere that way. And they're certainly above the weather and the clouds. It's also the era of huge computing machines. And as we all know, throughout our lifetimes, computers have got vastly more powerful than they were. I mean, there's more computing power in your watch than there was in Apollo 11. So the result of that is that we live in a golden era for science. Knowledge is rapidly advancing on many fronts. But if you were here last week, I explained then that there are still some pretty difficult puzzles. We're not there yet. We don't understand it all. So what we tell you about as modern astronomy is actually a snapshot in time. And I think some of it will have changed quite a lot within the next few decades, assuming we don't all blow ourselves up or fry the planet. But the big but of all, science is still observation led. The great theoretical advances always follow observational advances, or occasionally they come very quickly before the observation. I mean, the Big Bang, for example, was a theoretical prediction, though you might argue that it was following Hubble's observation of the expanding universe. So I still contend that you're never going to solve what the universe is by contemplation alone. It's all about observation. Thank you very much.
Well, thank you very much, Jane. A round of virtual applause, I think, for both our speakers, please. Excellent. So just looking at the chat, obviously both of you were extremely convincing and, in fact, compelling. In fact, someone has even said so, that you're an excellent speaker, Jane. We do have just the one question this evening, so far at least, from Ben. At least I think I'm reading that right. The font's a bit small. How did they prove that space itself is expanding rather than the galaxies are moving apart through space?
I think the answer is that space and time must have been created in this Big Bang event, and that space rapidly expanded at the start of it, and it's still continuing to expand. So I think that's really where the idea comes from. And it's built into, I mean, Newton had a theory of gravity in the about 1680, he published it, and that was the best theory of gravity we had until 1950, when Einstein published his theory of gravity, which is popularly known as Einstein's general theory of relativity. Now, in general relativity, what you do is you propose a quantity called a metric, which describes space and time. And then you kind of test whether that fits your observations. And it took, I suppose, 10 or 20 years for people to begin to propose metrics for the whole universe. There was one called the Einstein-de Sitter metric. There was another one called the Friedman-Robertson-Walker metric. And they made various different predictions. You know, some of them made a prediction that it would get bigger and then crunch back. Some of them made a prediction that it would continue expanding forever. And some of them made a prediction that it would expand more and more. And so you propose metrics in which space expands and they fit the data well. I think that's the answer.
Okay, thank you. We have had a second question that's just popped in from Matthew Hand. So no
yeah,
one
that's
knew
correct.
until the 20th
No one knew
century.
galaxies existed until the 20th century.
Well, I mean, presumably we knew that stuff like Andromeda and so on was there. We just didn't know what it was.
Well, yeah, there was I mean, it was Hubble who settled the argument, but there was quite an argument going on before that about whether they were part of our galaxy or not. And the artificial intelligence to see me moving my hand and put my thumb up. Right. So yeah, I mean, there was quite a debate about it. It was people like Captain in the Netherlands was one of in the sort of 1900s, 1910s. He was one of the first people who was able to sort of, put together a picture of a galaxy. You may have heard of a politician a few years ago called Lembit Erpik, who led a kind of mad sex life, and which was, tabloid headline fodder. Well, his grandfather was a great astronomer, Ernst Erpik, and he also had a mad sex life. He brought 2 wives with him when he fled from Russia. And he was quite a contributor to this. And in America, it was Harlow Shapley. Again, about that time, 1900s, 1910s. And these people were beginning to work out a structure of the galaxy and some distances. So then they could think about whether these nebulae, like what we now call the Andromeda Galaxy, were inside or outside the galaxy. And eventually Hubble answered the question.
Okay, thank you. In typical fashion, we've got about 3 minutes left, and 3 more questions have just pinged in.
That's great.
Oh, it's always encouraging. So I doubt any of these will be particularly quick to answer. So we've got.
Well, yeah, I could take. Are there any theories on how the Big Bang began? Yeah, there are. Read a book by Alex Vilenkin, and I'll look on my bookshelf in a minute and tell you the title. They're all purely speculation. There is no observation to back them up. But my take on it is that space and time were created in the Big Bang, so there can't possibly have been a before. And I think Stephen Hawking said that as well. So that's that one. What is space expanding into? Good question. Send your answer to the King of Sweden and claim your Nobel Prize. And how did Chandrasekhar discover the mass in which a white dwarf becomes unstable? He did this in the 1920s. That was when quantum mechanics appeared. And this was one of the first applications of quantum mechanics, because a paradoxical thing happens with white dwarfs. The more massive they are, the smaller they get. And he worked out a mass at which the radius is 0. And not to put some points on it, some bad stuff happens then. Typically they explode and turn into neutron stars.
Yes, I remember that much. Dividing by 0 is never a good idea. Well, that's covered the last of the questions. So thank you, Jane. Thank you, Gordon. Thank you all for joining us for episode 5. And we will see you back here next week for episode 6, the grand finale, if you will. And of course, the recordings will be available online if you would like to catch up on this or previous talks.
Here's Vilenkin's book, Many Worlds in One by Alex Vilenkin. I'll write that in the chat just quickly.
Thank you very much, Jane. So in that case, again, thank you all for joining us. Have a lovely evening.